Welcome to the lesson 35 of industrial instrumentation. We will start to discuss the chromatography. In general, actually we call it gas chromatography, though it is more popularly known, but it is actually it's a chromatography because the chromatography is both for the gas and the liquid. So in these lessons and subsequent lesson, that means lesson 36, we will consider the gas chromatography, we will consider the chromatography. Let us look at the contents of the lesson 35. Contents. We will basically have an introduction to the systems, what the actually chromatography look like, what is the packing materials used and what is actually where it is used, all those things we will discuss. You know, the chromatography is basically the separations of the fluids, because in many industrial situations as well as in the chemistries we need this type of situation when there is a mixture. So, we want to know, it is very difficult to know the content of the percentage content of the mixture of the two gases. So, in that case we can apply the chromatographic method to separate the two gases and find the percentage content of the individual gases or individual components when it is more than 2 and 3 components present in the gas, right. So, basically those things we will discuss how it works actually, what is the elutions we are talking about and how they actually will know from the peak of the curve that the percentage of the individual components of the fluids exist in the gas. So, those things we will know in this particular lesson. Introduction, then we have basic chromatography, we will discuss the basic chromatography here. At the end of the lesson the viewer will know what is the packed bed column and open tubular column, because we will see in the chromatography we will find that the basic principle is something like this, that we will send the mixture of the gas or fluid through a column, and it initially absorbs both the thing, absorbs or adsorbs both the mixture, but we will see that depending on the characteristics of the individual components it will elute, that means it will relieve or it will release the gas or fluid, okay, with the difference of time, right. So, that by that actually we can know, we can measure the contents or we can measure the concentration of the gas. So, this is the basic philosophy of the, we have different detectors, all those things will be discussed these lessons as well as in the lesson 36. So, we need that the column react, those tubular column or packed bed column, so through which the mixture will be passed. So, we will discuss what is the packed bed column and open tubular column. Then we have what are the different partition forces that are present between the solutes. Okay. Terms like partition coefficient, retention time, selectivity factors, all these things we will know in this particular lesson. How does the plate height, we will see the what is the height, plate height and the various other factors affect the column efficiency, because efficiency of column is very important, not only to know the contents of the individual components of the gas, because it depends on the material of the column, so efficiency of the column, it will also distinguish between the two contents, two components very nicely, otherwise it is very difficult to find the percentage contents of the individual components in the mixture. Quantitative analysis of the chromatogram, how we can make quantitative analysis of this gas chromatography or chromatogram, the plot which we will get from this chromatography we call it chromatogram. Introduction. Chromatography is a method used to separate or to analyze complex mixtures. The component to be separated are distributed between two mutually immiscible phases, stationary phases and mobile phase, which are brought into contact. So, there are two phases, these terms we will very frequently refer throughout this lesson, that means stationary phase and the mobile phase. The stationary phase forms the bed and the mobile phase percolates through it. So, we have a bed, we see the packed bed column and we are talking about. So, that stationary phase will make that bed and the mobile phase will percolates through it. Why do we use chromatography? Why do you need this gas chromatography or chromatography in general? Let us look at. It can separate complex mixtures with great precision. This is most important thing. right. I have two mixtures or two or three gases in a particular mixtures. I want to precisely know, that means first of all you have to separate. If you can't separate precisely, you cannot measure the contents of the individual gas, right. So, the precision in separation is also very important in the case of gas chromatography. So, that is the reason I am telling it can separate complex mixtures with great precision. Even very similar components like proteins varying only by a single amino acid composition can be separated. This is most important. People, I mean, in many cases we need this type of separations. Okay. So, different components, okay, different chemical compound with even with a single amino acid differences can be separated. This is a major contribution, since before the chromatography separating these biological compounds was extremely tedious and time consuming and unreliable. Okay, chromatography is quite reliable instrument in that sense. Chromatography can be used to separate very delicate products, since the conditions under which it is performed are not typically very severe. Okay, very delicate products also, that means its temperature is not very severe, that means it will that is reasons I am telling that it is not very typically not very severe, that means temperatures, moistures, everything is not very extreme. So, at normal room temperature you can do it. So, that is the reason very delicate compound, very delicate complex of the gases, okay, all those things can be nicely separated in this particular system. Chromatography is one of the most important analytical techniques, especially in the molecular analytical chemistry. Its coupling with atomic spectroscopy has extended its application to element analysis. So, with the advent of the with the advancements in the in the spectroscopy, atomic spectroscopy, we can identify the element analysis also, it can be used in the element analysis. The information obtained by the gas chromatography is not only useful for the researchers in organic chemistry or biochemist who wants to know what the material he or she has synthesized in the laboratory or separated from the living tissue, but also to the industrial scientists and engineers. Okay. That is the reason we are discussing in this course of industrial instrumentation. It has a tremendous application in industrial instrumentations, where we need to separate, okay, where we need to compositions of the gases, okay, especially compositions of gases is important to know. I mean, it is very important parameters in many situations of his own or competitor products, because suppose a unknown products is coming. So, we do not know what is the composition. So, with the gas chromatography we also know not only the percentage, but also know that what is the different composition of the gases present, right. Basic chromatography equipments. What is the equipment? Let us see this is the basic equipments. We have a solvent tank, we can see here. You see we have a solvent tank here, right. We have pump. So, through a pump we are putting it, and there is a feed injections, it is coming here, and it is through a column it is going. Now, we will see that how this column, because it will retain there for some time, after that it will dilutes, it will release one by one the gases. Okay. So, that will be detected by the recorder, and that will be ultimately recorded in a recorder, strip chart recorder, XY recorder. So, that type of cases we can find the, so from the peak we can know the percentage compositions of the gas, right. Column. What is column? The column is where the actual separation takes place. Okay. Separation of takes place. Usually initially all the column, all the gas will, all the mixture will go inside. So, it will retain depending on the properties. So, it will elute one after another, the gas one after another, right. It is usually a glass or metal tube of sufficient strength to withstand the pressures that may be applied across it, right. It contains the stationary phase and the mobile phase, which runs through the column and is adsorbed or absorbed on the stationary phase, right. Adsorptions or absorptions. Okay. So, it contains the stationary phase and the mobile phase, which runs through the column and is absorbed or absorbed depending on the stationary phase. There are mainly two types of columns. So, we have a packed bed column and open tubular column. So, let us discuss one by one. It is comprised of a stationary phase, which is in granular form and packed baked into the column as a homogeneous bed. The column is completely fed by the stationary phase, right. Open tubular column, here the stationary phase is a thin film or layer on the column wall, and there is a passageway through the center of the column. Okay. Through the center of the columns there is a passageway through which the feed will pass through, right. The mobile and stationary phase, these are two things we are repeatedly telling. The mobile phase is comprised of a solvent into which the sample is injected, right. So, mobile phase is a sample is a comprised of a solvent into which the sample is injected. We have seen in the figure, through a pump the solvent is coming and the sample is injected through, which is called the feed, okay, is injected through this one. So, this is the mobile phase, right. The sample and the solvent flow through the column together. So, these both the sample and the solvent flow through the column together, hence the mobile phase is often called a carrier fluid. So, sometimes we are calling it carrier fluid. The stationary phase is a material in the column for which the components of the sample to be separated have varying affinities, right. So, it should have varying affinities, otherwise you cannot separate, okay. That is the most important thing in the chromatography. So, that is the reason third bullet I am explaining. The stationary phase is a material in the column for which the components of the sample to be separated having varying affinities. Depending on the material which comprise the mobile phase, two general types of chromatographic process exist, okay. Depending on the material which comprise the mobile phase, two general types of chromatographic process exist, and they are gas chromatography depending on the mobile phase. Here the mobile phase is a gas and generally the gas is inert in nature, and the stationary phase is a adsorbent solid or liquid distributed over the surface of a porous inert surface, inert support. This porosity is very small, in the order of Armstrong, please note, right. This is important. This porosity, size of the porosity or the also will make the affinity of the different affinity to the different gases or components of the different gases, mixture of the gases. And the liquid chromatography, here the mobile phase is generally a low viscosity liquid which flows through the stationary phase bed, and this bed may be an immiscible liquid coated onto the porous support, a thin film of liquid phase bonded to the surface of the adsorbent solid or a solid of a control port size. Clear? Note, chromatographic types are classified according to the mobile phase material, since for different material different operation techniques and equipments are used. Operation, let us look at steps in the chromatography. So, you see here we are just change the directions. So, from the feed injections we are solvent is here, we are feed injections, it can be other way also. In this case it may come through gravity. So, other case we have to use a pump. So, basic operations in a chromatograph, this after this it will go to a detector, after this it will go to a after this it will go to a recorder. So, this is a detector, same thing, solvent, oven. So, it's if oven is necessary, suppose in some situations we have to use a control temperature. So, in that type of situations we need a oven. So, that is the reason we put in the oven, but if it's most of the cases we don't, the temperature is not very crucial. So, in that cases we can use the normal room temperature. Feed injection. The feed mixture of various components is injected into the mobile phase, okay. Obviously, it is a mixture of individual components. If it is a single gas, single component, obviously we are not going to use the chromatography or gas chromatography. Number 2, the mobile phase flows through the system under gravity or capillary action or action of a pump. So, there are three possibilities, either it will through gravity it will move, or through capillary actions it will move, or the actions of a pump it will move. Separation in the column. The different components of mixture feed have different rates of migration as the mixture is carried by the mobile phase over the stationary phase, right. These differential rates provide the separation between the various components. Repeated sorptions and desorptions takes place. I do not know whether it is desorptions is a dictionary, but where it is the opposite of the sorptions, takes place during the movement of the mixture over the adsorptive material determining the rates. Elution from the column, you see, after the sample is displaced from the stationary phase, the different components in the sample will elute from the column at different times. This is the most important thing in gas chromatography, right. Sample will elute from the column at different times. If it is not in different times, we cannot separate, okay. Since it is coming at different times, we can separate, we can know the percentage, we can know the individual concentrations of the gas component, right. So, this is most important terms on gas chromatography. elute. The smaller the affinity attraction a molecule has for the stationary phase, the shorter the time spent in the column. Okay. So, obviously, you will find that there will be lesser affinity, I mean affinity will be different. I mean if you measure the affinity, so it will be affinity, one has a larger affinity than other. So, this will make our separation possible, otherwise the separation was impossible. Thus, the least retarded component elutes first, okay. The least retarded components elute first, at most strongly retarded components elute last, okay. It will come at the end and the most least retarded component will come at the first. Separation is achieved when one component is retarded sufficiently to prevent overlap with the zone of an adjacent solute as in sample components elute from the column. This is most important thing. Okay. If there is an overlapping, there is a problem. So, separation is achieved when the one component is retarded sufficiently. Okay. So, this is the word you see, sufficiently to prevent overlap with the zone of an adjacent solute as a sample component elute from the column. We will see later on it will come like this one, okay, peak like this one. However, if the curves looks like this one, it is very difficult to, okay, it is very difficult to separate. So, that cases. So, that is the reason we are taking sufficiently to prevent overlap. So, there is a sufficient gap or time with the zone of an adjacent solute as sample component elutes from the column. Detection. The different components emerging from the columns are collected, okay, and then the concentrations and the characteristics, this is the most important. The concentration and the characteristics of each component are confirmed by using some analytical procedures like infrared IR spectroscopy or nuclear magnetic resonance NMR techniques. So, we can identify the element, we can find the concentrations. Okay. So, the concentrations and the characteristics of the gas which is coming out, which elutes obviously with the time difference when it is coming out, I can measure it, I can detect the elements also. Now, for an example, we consider a mixture of components x, y, z. 3 gases are there, 3 components are x, y, and z. Initially, as the mixture is just injected into the column, there is no separation between the 3 components. Okay. Let us see, otherwise it is very difficult. Okay, you see here. So, in the mixture you see initially 3 gases are here. This is the time axis we are plotting. Okay. This is the time, x axis is the time, y axis is the separation between the 3 gases. That means elutes. You see, as the time goes by, x, y, z, the two, x has the least, z has the least affinity. So, it is coming out fast. You see, as the time goes by, okay, so the separation between the, separation means the time required, time needed to come out of the column is more and more, right. So, 3 components. Now, here the 3 components are mixture, x, y, z, 3 are mixture. Here you see as the time goes by, so the separation, that means the elution time is becoming more and more. So, it is coming out of the gas. So, one by one. So, z will be detected, then y will be detected, then x will be detected, right. So, I can go back. Consider a mixture consisting of a 3 component x, y, and z. Initially, as the mixture is just injected, when it is just injected in the column, there is no separation between the 3 components that we have seen. There is no separation between the 3 components. As the mobile phase drives the mixture down the column, a small separation becomes evident. When the mobile phase is moving through the column, a small difference, small separation becomes evident between the 3 components, which is shown in figure 3b. Let us assume that the speeds with which the 3 components moving is Sj more than Sy more than Sx, where Sj is the speed of the component z, where Sj is the speed of the component z, and Sy is the speed of the component y, and Sx is the speed of the component x. In other words, x has a maximum affinity. Okay. So, affinity is different for the different components, where z has the least affinity. This is shown in figure 3c. Thus, z will emerge from the column first, followed by y and followed by x. This is given in 3D. This is the things which we are. There is a mixture, there is no separation. When the mobile phase is moving through this one, slowly there is a separation. Okay. So, at the end there is a large separations between separations, that means of the elution times. That means elution times becoming more and more. In the case of X, his retention time is most, and in the case of Y, the retention time is medium, and in the case of Z, retention time is minimum, right. So, there is a arithmetic representation of my example. Chromatic behavior of a solutes, let us look at. Partition coefficient, there is some terminologies we are going to introduce. Partition coefficients or equilibrium coefficient is defined as the molar concentration of analyte in the stationary phase divided by the molar concentration of the analyte in the mobile phase. Analyte means the samples which we are going to make the analysis, right. But K is given by concentration in stationary phase upon concentration in mobile phase. You see, here is the chromatogram we are talking about, the plot. You see here are detected signal. Okay. So, x axis we are plotting time. You see the retention time, this is the time, because after injection. So, see when it is elutes, the Tm is coming first, then Tr will coming, okay, with a peak. So, these are the two peaks. So, this is called this type of plot is called the chromatogram in the case of gas chromatography. Retention time, okay, you see the here we have written Tr and Tm. Retention time, the time between the same sample injection and analyte peak reaching a detector at the end of the column is termed as the retention time. Okay. So, is the time between the sample injections and analyte peak reaching a detector at the end of the column is termed as retention. That means, here it reached the detector. Okay. So, here from here it reached the detector. Tm is the time taken for the mobile phase to pass through the column is called Tm. Time taken by for the mobile phase to pass through the column is called Tm. Okay. So, this individual gas we have shown, one component of the gas we have shown that it is retention time Tr, and Tm is the time. Obviously, we can see that the Tr is obviously that Tr should be more than Tm in all the cases. So, time taken for the mobile phase to pass through the column is called Tm. So, we will get similar graph, similar type of Tr, that means we will get similar Tr. This is for one gas, we can get, we will get this for the several other gas or the mixture of the components. Each analyte is a sample, in a sample will have a different retention time, right, that is I am saying. So, this we are showing for a single element. Okay. So, there will be, if you have a two such gas, gas which is making a mixture. So, we will have two retention time Tr1, Tr2, if you have 3, so on, right. Retention factor K dash, this is another, it describes the migration rate of an analyte on a column. Okay. It is also called the capacity factor, K dash equal to Tr minus Tm by Tr. Okay. Obviously, it is a positive because Tm is always less than Tr. When an analyte's retention factor is less than 1, elution is very fast. Okay. That is very undesirable. Elution should not be very fast. If the elution is fast, so it is very difficult to analyze, make the analysis. Typically, ideally, or I should say typical retention factor for an analyte is between 1 and 5 or to be 1 and 5. Okay. Selectivity factor alpha, it describes the separations of the two components say A and B on the column. It describes the separation of the two components say A and B on the column. Alpha equal to K dash B upon K dash A. Okay, two components we have K dash B and K dash A. Alpha is greater than 1 always, therefore, in the above equation we have assumed A elutes faster than B. So, A is coming out faster than B. Column efficiency, band broadening and the resolution, these are the important parameters. A solute zones pass through the column, they broaden and the concentration at peak maximum gradually falls, right. This will be more important, more clear when you show the graph. This broadening is important as it ultimately affects the resolutions. Okay. That means how close the characteristics, in the case of suppose the measurements, suppose I have a voltmeter. So, resolution means what? What is the minimum voltage of separations it can detect, whether it can detect 2.77 and 2.776 volt or only 2.7 or 2.6 volt. Okay, obviously, the voltmeter which can have a resolution of which can measure 0.001 volt. So, obviously, that will be preferred. Similarly, in this case also, in the case of resolution 2 it is a broadening, if it is broadened. So, it is obviously we say the resolution is poor. So, broadening is important as ultimately affects the resolution. If the broadening is higher, the resolutions will be poor. The solute zones should be kept as narrow as possible by proper design. So, we should have a very narrow zone, so that the peak will be very sharp. Plate height, there is another parameters will include here. Plate height is the quantity that measures the column efficiency and is related to the plate width. We will show this, what is the plate height and plate width. It is a prime measure of a peak dispersions in chromatography. It is a prime measure of peak dispersions in chromatography, which is given by H equal to L by 16 omega B upon TR dash whole square. What is this legend? Let us explain. Where L is the column length, omega B is the peak width, and T dash R is the retention time corrected for the transit time of an unabsorbed or non-retained solute. Okay. The theoretical plate model of the chromatography, we are assuming in the theoretical model we are assuming there is a separate plates remains there, but actually it is not, it is a mixture. So, the plate model suppose that the chromatographic column contains a large number of separate layers called the theoretical plates, right. Now, separate equilibrium of the sample between the stationary and the mobile phase occurs in these plates, clear. So, separate equilibrium of the sample between the stationary and the mobile phase occurs in these plates. We are assuming there is a separate plates. The analyte moves down the column by transfer of mobile phase from one plate to the next. Okay, one by one we are assuming that there are several plates. So, one plate to another plates, the analyte is moving with the presence of the mobile phase. It is important to know that the plates do not exist, they just serve as a way of measuring the column efficiency, because the column efficiency is very important. N equal to 5.55 TR square upon omega squared, omega half to the power square. What is this? Where omega half is the peak width at half height. Okay, it is the peak width at the half height, and N equal to L by H. Now, one more equations we will introduce is the Van Demeter equations for plate height. A more realistic descriptions of the process at work inside a column takes account of the time taken for the solute to reach the equilibrium between the stationary and the mobile phases, right. The resulting band shape of the chromatographic peak is affected by the rate of elution and the different paths available to solute molecules as they travel between the particles of stationary phases. Now, considering the various mechanisms which contribute to the band broadening, we arrive at the Van Demeter equation for the plate height, which is given by A plus B upon U plus Cu. Okay. This is all the dimensions of length. You see, we will explain this ABC in the next, where U is the average velocity of the mobile phase. A, B and C factors which contribute to the band broadening. What are these ABC? Let us explain. So, these are the factors, because band broadening will control the resolutions. So, how closely the two elements are there. So, how close the elements are in characteristics which we can separate, right. So, this we have to discuss here in this particular. So, ABC factors, A, B and C are the factors which contribute to the band broadening, clear. Now, A is actually what are the factors? Let us three factors we talk about. A is the eddy diffusions, it is in meters, okay, it is the diffusions in meters. The mobile phase moves through the column which is packed with stationary phase. Solute molecules will take different paths, though the stationary phase goes at random. This causes broadening of the solute band since different paths of different lengths. Okay. So, it is actually making different paths. We cannot restrict a single path, because there is a definite width or definite diameter of the column. Okay. So, this will make a different part. So, it will reach at a different, so that will make the different the broadening of the band. So, the length which you are talking about, okay, length in the chromatography, okay, it is not exactly the height. If it comes straight away from the bottom to the top, so we can say that it is a XLA, but if it comes suppose this way or something like this one, so obviously it will length will be different. So, there are innumerable, I mean number of path through which the liquid can go move through the column. Longitudinal diffusions, this is again the problem. So, okay, so we are always talking about the lateral diffusions, we have longitudinal diffusions which is meters square per second. The concentration of the analyte is less at the edges of the band than at the center, okay, at the center. So, it is less. Okay, so, obviously, if it is not homogeneous mixture, because it is a mixture after all, it is not a compound, that is entire this column that through in which we are actually putting the all the materials, okay, which actually absorbed or adsorbed and elutes the gases or liquids, right. So, obviously, it is very difficult to make the concentration. We are assuming that the concentration of the analyte is less at the edges and band than at the center. Hence, analyte diffuses out from the center to the edges, causing band broadening. Okay. So, it is going out to the, so this band broadening is there. If the velocity of the mobile phase is high, then the analyte spends less time on the column, okay, which decreases the effects of the longitudinal diffusions. Is high, then the analyte spends less time on the column, which decreases the effects of the longitudinal diffusion, right. Now, resistance to mass transfer, which is component C. The analyte takes a certain amount of time to reach equilibrium between the stationary and the mobile phases. Okay, it takes a certain amount of time to reach equilibrium between the stationary and mobile phase. If the velocity of the mobile phase is high, the analyte has a strong attraction for the stationary phase. Then the analyte in the mobile phase will move ahead of that in the stationary phase. The band of analyte is broadened now again. Okay. So, you see here, so the a typical Van de Meter plot. So, minimum plate height is like this one. So, we are saying that assuming the plate height is like this one, optimum velocity will give you this one, right, which will make the minimum plate height. Resolution is another important factors. Another measure to know how well the species have been separated is provided by the measurement of resolution, right. The resolutions of the two species A and B is given by R equal to TRB, retention time of the component B minus retention time of the component A upon 0.5 plus omega A plus omega B. Scale up of chromatographic columns, because depending on the different dimensions and the volume of the liquids, you have to scale up. Now, there is some typical formula how we can scale up that, because I have the existing column, laboratory model. If I want to use it industrially with a large analytical quantity and volume flow of the gases, so obviously I have to increase the dimensions. So, I have to think of dimensions, how will I choose this diameter and the length of the column, that is to be discussed now. During many instances, it becomes imperative to increase the size of the chromatographic column in order to increase the production capacity of a process. Doing so will require a scale up of the column to suitable size for the job. The scale up of chromatographic column is obtained by maintaining the same column length and increasing the cross sectional area. So, we are changing the cross sectional area, increasing the cross sectional area. Okay. So, the length remains same. So, I am changing the cross sectional area by a formula. Let us look at a simple way to calculate the scale diameter is given by the following equations. We have a load 2 upon load 1 equal to radius 2 upon radius 1 to the power square. What is load 1, load 2? Let us look at, where load 1 is the present volume of the column, okay, it is the present volume of the column, and load 2 is the desired volume of the column, or is the present volume of the column and desired volume of the column. Radius 1 is the present radius of the column. Okay. Obviously, 3 is in the equations, 4 are unknown, 4 parameters, 3 are known. So, obviously, radius 2 can be calculated. It is a calculated radius of the column. Okay. So, we can calculate and accordingly I can change. Very simple formula, though I mean with some limitations obviously. To recreate identical operating conditions on the scaled column as the unscaled one, the linear flow rate must be kept constant. Okay. The flow rate must kept constant. Okay. We should have flow meters to know that, I mean, because the feed, okay, mobile phase is moving through this one. The volumetric flow rate required for keeping the linear flow rate constant is given by volumetric flow rate 2 upon volumetric flow rate 1 equal to load 2 by load 1. Okay. So, obviously, we know that here in this case we have volumetric load 2, from this we can calculate the parameter. What is where volumetric flow rate 1 is the present volumetric flow rate, that is for the laboratory models, and volumetric flow rate, calculated volumetric flow rate, that is we can calculate. Okay. Now, quantitative analysis, this is also very important in the case of gas chromatography, right. Let us look at that. Peak area integration, what is that peak area integration? Let us look at. In column chromatography, the analog signal generated by the detector is graphically recorded in the form of a chromatographic peaks, right, which is called the chromatogram, that we have seen. It looks like this. Okay. So, it is coming like this one, if I take. We have seen it is coming like peak like this one, right, peak like this one. So, this is called the chromatograph, right. The area under these peaks can then be integrated in a variety of ways. Okay. So, we are integrating that areas and the resulting data related to the composition of the samples can be studied. This is most important thing. Now, we come to the detector side. Once we have, I mean, with some detectors we can collect the analog signals, electrical signals. Okay. Now, it will be plotted, right. So, the area under these peaks can then be integrated in a variety of ways and the resulting data related to the composition of the samples can be studied, right, because the area will give you the relative contents of the different compositions. The ways in which the area under the peak can be calculated are as follows. There is various method by which areas can be calculated. We will discuss one by one. Height times width at the half height. Height multiplied by this basically height multiplied by the width at the half height. What is that? It involves multiplying the actual peak height with the width of the width at the half height, right. It looks like this, that means I will show you actual peak height. Suppose you have a peak height is this, okay. This is multiplied by the half height, width of the half height, you multiplied by this. Suppose this is x, this is y. So, x into y is the height times width, okay. Height times width at the half height will give you the measure of the integration. A new baseline is drawn for measuring peak height and the width of the half height, since the normal zero signal baseline causes large deviation due to tailing, right. Planimetry, this is another method of integration. In this method, the peak is traced with a planimeter, a mechanical device which measures area by tracing the perimeter of the peak. Okay. In this method, the peak is traced with a planimeter, a mechanical device which measures the area by tracing the perimeter of the peak. Planimetry is less precise than the height width integration due to errors caused from the placing the baseline, tracing the peak outline and obtaining a rating. Triangulation. In this method, tangents are drawn to the sides of the peak at the inflation points. In the area of the triangle formed by these tangents and the baseline is determined. Okay. So, it looks like this. I have a peak, here. Okay. Okay, I should not do. So, I am drawing a tangent here, tangent here. So, we will give you the area of the triangle will form this and the baseline is determined, right. So, tangents we have drawn, one at the inflection point like this one, inflection points rather. So, we are drawing two tangent where it meets. So, we are making one triangle. So, that area of the triangle formed by these tangents, baseline is determined. The height is measured from the baseline to point where the tangents intersect, right. Ball and disc integrators, this is a very mechanical integrator, is useful. The ball and disc integrator shown in figure 6 in next figure is an automatic mechanical type of integrator. A ball positions on a rotating flat disc will rotate at a speed proportional to the distance from the center of rotation. The ball is positioned on the disc at a distance from the center in the same relationship as the position of the recorder pen to the baseline of the chromatogram. If the disc is rotated at the constant speed, then the ball will rotate at a speed proportional to the position of the recorder pen from 0, right. The speed is then transmitted to a roller through a second ball, which by means of a spiral in and spiral out cam actuates the integrator pen at a speed directly proportional to the position of the recorder pen. Clear? We will more clear once you show the diagram. The drive between the disc and the ball is by traction through an oil film, which is similar to the induction motor, where slip is proportional to the driven load. Reading the integrator trace shown in figure 10 is done as described in the following points. First step is to establish the desired chart time interval from the recorder pen trace of the chromatogram and the project directly down to the integrator trace. The value of an interval is obtained by counting the chart graduation crossed by the integrator trace. Okay. So, it will be like this one, we will see, it will be like this one. So, it will be graduation crossed by integrator trace. Okay. So, interval is obtained by counting the chart like this one. A full stroke of sawtooth pattern in the either direction presents 100 counts, and every horizontal division has a value of 10. Okay. So, full stroke of the sawtooth pattern in either direction represents the 100 counts and every horizontal division has a value of 10. Values less than 10 are estimated, that means is only 10 is minimum resolutions we can get. So, if it in between comes anything, that is to be estimated. In the example, the interval for the main peak is 1084 counts. You see, this is the disc and we have this pen is going to a recorder that I am not showing. Spring, there is you have a ball and the disc, this input linkage is here, this is a pulsar and this is a roller, okay, and these are time motors. So, it is going to the pen. In the next graph we will show, you see here this pen goes here, which is recording on a chart, right. So, ball and disc integrator schematic. So, this is about the gas chromatography basic recorder. Okay. Let us look at the plot now. You see there are total 1084 counts from 0 to 1083. So, we estimation on the peak areas with ball and disc integrators. Okay. So, we have making 10 divisions here. So, each has a 10 counts here. So, we will get 1084 counts here. Okay. So, with this we can estimate the peak areas of the gas chromatography, peak areas of the systems. Okay. Now, gas chromatography, as you know, it is extensively used not only for analytical, because as the beginning we said that the initially it is not only for making the analysis of the gas mixtures which is coming out in some industrial process, but also to know, suppose there is some other company is making some particular mixture of gases, what is the components of the gases. It is very vague, though it is very difficult to tell. Now, once you separated the gas components, obviously you can make the analysis, you can several other method to know what is the component, but the basic separation is the most important thing. When you have to eat one by one, it will come. So, basically I can say that this chromatography is something like that. If I pass the gas mixtures through a column, whether it is open channel, open tubular form, or a flat bed reactor, flat blade column. So, it will absorbs or adsorbs for some time, or it will retain the gas for some time, then it will slowly, all the gas will not come out immediately, okay, or not, it will come after certain amount of time, it will come one by one from the packed bed column. So, this actually makes our gas chromatography feasible, right. Now, in this case, one thing we should know that it has a tremendous, not only in the chemistries, it has a tremendous use in the industrial operations. In many situations, we have to trace the presence of gases or the gas mixtures with the process. So, that type of situation we can collect a sample gas, okay, and inject through this one through the in a feed, because we have seen that we have a stationary phase and the mobile phase. Okay, so this will go through the feed as a feed to the system, so the carrier to the system. So, slowly it will separate and it will tell the composition. Now, different compositions, determination of the percentage and all this thing, that is coming next, that is not, we are coming later on, but the basic difference, basic finding that the presence of particular gas or composition of detecting the particular gas or the components of the gases is most important. Later on, you can use the spectroscopy and all these things, find what are the elements of the gases are there, mixture of the gases there. First, the separation. So, this is the only method the mankind so far developed. It is a very excellent method as so far to find the making the separations. Okay, before that, as I told you, it is very unreliable method. This is a quite reliable method, and it is not that simple, sensitive to temperatures, and although in some cases we have to maintain the particular temperature while you are calibrating, but in most of the cases the temperature, maintaining the temperature is not very crucial. That is the reason you were saying it is not necessary, it is not very harsh, it is not very severe environment while you are. So, in many cases, suppose some gases, suppose it is getting decomposed, okay, or in some other particular temperature, that type of cases also we can use the separation. In other method, you can have high temperatures and all this or low temperature, those things are not necessary in the case of gas chromatography. So, with this I come to the end of the gas chromatography 1, and in lesson 36 we will continue with this particular of the chromatography, which is the chromatography 2. Welcome to the lesson 36 of industrial instrumentation. This lesson is a continuation of the lesson 35, where we have discussed the chromatography 1. In this lesson, we will discuss chromatography 2. So, let us look at the contents. This is a chromatography 2, as I told you. The contents are gas chromatography, liquid chromatography, chromatogram. Okay, so, we will see that in this particular lesson, so we will discuss how the chromatogram should look like, and what are the, if there are multiple peaks comes, and what are the problems, what exactly the shape of the chromatogram should be. That depends the finding the concentrations of the different components of the gas and liquids precisely. At the end of the lesson or end of the chapter, the viewer will know different equipments and different operation techniques used in gas and liquid chromatography, different detectors used in the chromatography and their purpose and their classification. We will find there are different types of detectors available. There are thermal conductivity detector, there are film ionization detector, there are electron capture detector. So, there are different, the principles are somewhat different, though the thermal conductivity detectors are the oldest one and most widely used detectors in the gas chromatography, but we will discuss the other detectors also, where you will find that we will making a derivatives of the particular element of the mixture, so that to find the concentration accurately. How do operating conditions like pH value, temperature affect the chromatogram? Okay, so we will find these things also, the pH value, though it's not very important in the case of gas chromatography, this is very important in the case of liquid chromatography. Gas chromatography, already that we have discussed. Gas chromatography makes use of a pressurized gas cylinder and a carrier gas such as helium, which is inert in nature, to carry the solute through the column, because we will find, we have discussed this thing, that there is a column and through column this the gas should flow, right, and there is a packing material inside the column. So, which will absorb and elute it after some time one by one. Gas adsorptions, that is gas solid chromatography, involves a packed bed comprised of an adsorbent used as a stationary phase. Common adsorbents are zeolites, silica gel and activated alumina. These are the most common sort of adsorbents are used in the chromatography. This method is mainly used for separating mixture of gases. You will find this is basically used for the mixture of gases, right. Gas liquid chromatography is a more common type of analytical gas chromatography. In this type of column, an inert porous solid is coated with a viscous liquid which acts as a stationary phase, and diatomaceous earth is the most common solid used, and solutes in the feed stream dissolve into the liquid phase and eventually vaporize. Current flow across the external resistor is sensed with a voltage drop and is amplified and displayed on a recorder. Now, hydrocarbon groups are introduced into the flame and a complex process takes place in which positively charged carbon species and electrons are formed. Now, the current is greatly increased. Okay. Now, this flame ionization detector responds only to the substance that produce charged ions when burned in a hydrogen air flame. So, that is most important thing. In an organic compound, the response is proportional to the number of oxidizable carbon atoms. So, this is basic principles of the flame ionization detector. Now, if I look at the thermoionic emission detector, you see this is thermoionic emission detector. It is principally something different. It employs a fuel poor hydrogen plasma. This low temperature source suppresses the normal flame ionization response of a compounds not containing hydrogen and phosphorus. Although the response to carbon is not entirely eliminated, a non-volatile rubidium silicate bead, here you see here non-volatile rubidium silicon bead centered about 1.2 centimeter above the plasma jet is electrically heated by variable current supply to between 600 to 800 degree centigrade. This arrangement permits the fine adjustments of the bead's temperature and independent of the plasma as a source of thermal energy. With a very small hydrogen flow, the detector responds to both nitrogen and phosphorus compounds, and enlarging the plasma, the changing the polarity between the plasma tip and the collector, and detector responds only to the phosphorus compounds. Okay, so that I can make it nitrogen, I can make it sensitive to the phosphorus compounds also. Now, compared with the flame ionization detector, the thermal emission detector, thermoionic emission detector is about 50 times more sensitive for nitrogen, okay, and about 500 times more sensitive for phosphorus. Okay. So, any traces of phosphorus, any traces of nitrogens can be better detected in the case of thermionic emission detector compared to the flame ionization detectors, though flame ionization detectors also is a comparatively new compared to the thermal conductivity detector. The minimum detectable limit is around 0.06 Pg per second for nitrogen. Okay. So, this is the thing you can see here, that there is a flame tip which is around 1.2 centimeter above the plasma jet. Okay. So, this is our thermionic emission detector. Last we will discuss the electron capture detector. You see, this is the electron capture detector. Now, electron capture detector has two electrodes within with the column effluent passing between. One of the electrodes is treated with radioisotopes that emits high energy electrons as it decays, and these emitted electrons produce large amount of low energy thermal secondary electrons in the gas chromatography carrier gas, all of which are collected by other positively polarized electrode, either of the positive polarized electrode. Molecules that have an affinity for thermal electrons, captured electrons as they pass between the electrodes and reduce the steady state current, thus providing an electrical reproductions of the gas chromatography peak. Of the two general designs, the plain parallel and the concentric cell and the latter design is preferred, since it is easier to construct a small low loaded volume cell in this form. Now, particular radioactive sources which are used, the tritium adsorbed in the titanium or scandium and nickel 63 as a foil or plated on the interior of the cathode chamber. So, your chromatograph will change. So, obviously, if the chromatograph change, efficiency, selectivity, everything will change. So, this used to be, so precise what are the desired value of the chromatogram, that is to be maintained, right. Fourfold information is obtained from the chromatogram. What are the different, components I am getting from the chromatogram? What are the different, informations I am getting from this chromatogram? Right, already we have discussed, but let us jot down, right, one by one. The level of complexity of the sample is indicated by the number of peaks. How many, what is the complex mixtures? That we can detect from this one. So, level of complexity of the sample is indicated by the number of peaks which appear. Qualitative information about the sample of composition is obtained by comparing peak positions with those of the standards. Okay. Qualitative information about the sample composition is obtained by comparing the peak positions with those of standards. Quantitative information regarding the relative concentrations, this is most important. So, we are measuring relative, because the sample, if we are not absolute measuring, we are making the relative comparison, relative concentrations actually we are measuring in the gas chromatography, okay, because otherwise we cannot measure it, because we need the injections and it is only 10 microliter, that is the best. Smaller the sample, better is the detection. Sorry. Quantitative information regarding the relative concentration can be obtained from the peak and area comparison. Column performance can be checked by comparing with the standard outputs. Okay, this column performance also, because if I know the particular, suppose if I want to calibrate the column performance, I know the particular gas which actually we are injecting. Okay, so that time when unknown gas is coming, if I want to calibrate how the column actually working. So, the column efficiency can also be can be known by looking at the chromatograph. So, these are the four features which we will get from the gas chromatograph. The most important thing is the relative, first of all, what are the different components of the gas present in the mixture. Second thing is the relative, this is the most primary importance. Second thing is the relative concentrations of the gas or liquid or whatever it may be in the mixture. Okay. So, with this I come to the end of the lesson 36 of industrial instrumentation.